Okay, hello Analysis 1A, back for more. We gotta make some progress. Here we go. We have spent, I don't know, like a day-ish, less, talking about limits, and mostly we took a casual approach. The approach of just kind of thinking about what a limit means and just sort of doing it. Let's take now a more serious approach. So this is something I normally like to do live. I think it's really fun to do live, but maybe this is also just okay. So we'll find out. Here we have a limit. The limit as x approaches 1 of 3x plus 2. And okay, of course this is just 5. And alright, it's because this is so easy, maybe you might even almost say boring, that it's a good place to start our investigation. And so we can do this. Let's go. What does this thing look like? Well, it's a line, 2, 3, 4, 5, and here's 1. And okay, when x is 0, we're here at 2, and then by the time we get to 1, we're up at 5. And so, yeah, this is really just this line, and sort of there it is. Okay, so this is a function. You could say. So we have the function f of x equals 3x plus 2. And now what I want to do is sort of an investigation or a discovery or something like that of what we really mean when we say the limit as x approaches 1 of 3x plus 2 is 5. And this is going to be kind of to some extent, a repeat of some stuff that we did last semester in Pre-Calc C. So hopefully it will be familiar enough that it's okay to do this via video. Alright, well, let's go. What do we mean intuitively? Intuitively what we mean is that the limit as x approaches 1, when we ask the limit as x approaches 1 of 3x plus 2, when we say that it's 5, what we mean is that when x is really, really close to 1, the function is really, really close to 5. But how close to 5 is it? And the answer is, it is as close as you want. The very, very kind of low-level understanding of what we claim we are making when we say that the limit is 5, what we really mean is that I can make this function as close to 5 as you want. And so there is this kind of back and forth dialogue reminiscent of what we did last semester, in which I say, the defender of this claim, the limit as x approaches 1 of 3x plus 2 is 5. And someone asks me, well, what does that even mean? And I respond, well, it means that if x gets close to 1, this function is really, really close to 5. And then this person is entitled to ask, how close? How close to 5 is this function? And my response to that person is, as close as you want. This function is as close to 5 as you might possibly want it to be. And now it's up to my skeptic that I'm talking to issue a challenge. And the challenge comes in the form of some kind of number, and it's a demand on how close to 5 I need to be. And okay, perhaps the challenge might be like, 0.1 or something like that. Okay, so in other words, what this person has demanded is that I get within, let me just call it 1/10 of 5. Okay, so just to kind of take it from the top, I say that the limit as x approaches 1 of 3x plus 2 is 5. We all kind of know what that means. It means that, near x equals 1, this function is near 5. But what precisely does it mean? You ask. My response is, near 1, this function is really, really close to 5. How close? Asks the skeptic. Answer, as close as you want. And now the skeptic says, okay, I dare you to be within 1/10. And now, intuitively, what must I do to meet this challenge? To meet this challenge of 1/10, remember, I'm claiming that near 1, the y value, the output of this function is near 5. And so if someone says, okay, I dare you to get within 1/10 of 5, then what I must do is get close enough to 1 so that the outputs of this function are within 1/10 of 5. So what I need to say is, how close to 1 do I have to get in order for that to be true? Now, this is maybe a little bit of a tricky question, and we can kind of think about this for a while. I think if we were doing this live, someone would maybe even have an answer. And the answer is, okay, contrary to this line, which doesn't look so good, to be honest, contrary to the way this line looks, this line has a slope of 3. And the fact that this line has a slope of 3 is kind of relevant, because what it means is that if here I am at this point 5, if I go over, say, 1, then I have to go up 3 to land back on this line. Duh, that's of course what slope means. And if I go 1 backwards, then I have to go down 3 to get back into this line. So understanding that this line has slope 3, how much kind of wiggle room am I permitted here? And well, the answer is not that much, right? If I am only allowed to be off by 1/10, then if this line has slope 3, how much can I kind of scoot over before I break free of the parallel lines? And I think it's clear in this case that the answer is 1/30. Because if I go over by 1/30, then that will already sort of break me free of these lines. And so there is kind of this challenge of 1/10 that's been issued. I'll kind of write it right here. The challenge was 1/10, and the response was 1/30. And now I think it's just true that as long as I remain within 1/30 of 1, then because the slope of the line is 3, my y value will be off by at most 1/10. Okay, and well, we can sort of keep playing this game. What if I was given maybe a different challenge? Maybe this is kind of almost easier to see. But what if my challenge were all you have to do is be within, say, 1/2? Well, if all I had to do was be within 1/2, how close to 1 must I get in order to be only within 1/2? And the answer is, if I was challenged with 1/2, then I think I can get within 1/6. I think that's kind of good enough. This is supposed to be kind of obvious from the geometry of the picture that as long as I stay within 1/6 of 1, then because those x values are being multiplied by 3, then my y values will be off by at most 1/2. And okay, if instead I get challenged with 1/100, say, then how much wiggle room do I have? Then the answer is much less. But I think the answer is in fact 1/300. Okay, and so what's happening here is it's this kind of game. It's this game of me precisely indicating what I mean when I say that the limit is 1. And what I mean is that no matter how close to 5 you demand I be, I can get sufficiently close to 1 to meet that challenge. You challenge me, you say, I dare you to get within 1/2 of 5. Well, I just merely go within 1/6 of 1, and within 1/6 of 1, the outputs to this function will be within 1/2 of 5. If you dare me to be within 1/10 of 5, then I get within 1/30 of 1, and within 1/30 of 1, my outputs will be within 1/10. And finally, what's still on the picture right now is if I'm issued a challenge of 1/100, then I can stay within 1/300 of 1. So this is like 1 plus 1/300, and this is like 1 minus 1 over 300. Okay, and so it's time now to kind of do this in general. We call this challenge number, like we did last semester, epsilon. And epsilon is just the Greek letter that we use for a very small number. And here, if I am challenged with a very small number, epsilon, I think that it is clear here that because this line has slope 3, that I am allowed to wander off by 3 over epsilon. And as long as I stay within 1/3 of epsilon, then my output will always be within epsilon of 5. And so this number we also have a name for. We call it delta. And what is delta? Delta is another Greek letter which we use to refer to how far away from 1 I'm allowed to go in order that my function land within epsilon of the number I'm claiming to be the limit, which is 5. All right, I don't know if this was the greatest explanation ever, but this is kind of the idea. And so what we have now is this new kind of definition. Let's do this. We have this sort of formal definition finally of what it means for a function to have a limit. And the idea is like this. I have some function, and I want to know the limit as x approaches a of this function. And suppose I want to say that this limit is L. Okay, informally, and to be totally honest, an informal understanding of what limits are is actually sufficient for most kinds of things that we want to know. So usually we can just go with our kind of gut feeling about what these limits are saying. And all they're saying is, dude, very, very near A, the outputs of this function are very, very near L. That's just kind of what it means to say that the limit is L. But if we want to be very, very precise, and there are some times when we really do want to be very precise, then we can lean on this definition. And okay, what just happened in this video is a little sad to do this via video, but what happened in this video was a kind of exploration of the true sort of meaning of what we mean when we say that the limit is L. And this is kind of what we came to. So here's the picture. Cha-cha-cha. And there's some kind of function. And who knows, what this function looks like, because we're doing this now in general. So here is A. And actually, just to kind of prove a point or something, let's just suppose that this function actually doesn't even exist at A. Because, just recall that when we say that the limit is L, we are not actually talking about what the function is doing at A. We are talking about what the function is doing near A. And so we're speaking about, we're really asking, very, very, very close to A, what kinds of numbers is this function outputting? And the answer is this function is outputting numbers which are very, very close to L. Okay, and what precisely do we mean when we say that? Well, this is the definition. The definition says that, that the limit is L if the following is true. No matter what kind of skeptical challenge I am issued, and that challenge comes in the form of this tiny number, epsilon. Epsilon is a demand. It's a demand that the y values be within a certain very small interval around L. So if I'm claiming that the limit is L, then your response is, I dare you to get within epsilon of L. And my claim, of course, is that near A, this function is near L. And after receiving your epsilon challenge, I have a response. And the response is I go as close to A as I need to. And delta is the number which indicates how close to A I need to get in order that all of the outputs of my function are within epsilon of the number I'm claiming to be the limit. And so the idea is that when I plug in any of the x values in this interval, and here I will just be clear here that, remember, what's happening at A is not under discussion, but any number that is in between A minus delta and A plus delta, exclusive, not counting A itself, the claim I want to make about these, about all of those x values is that when I plug them into my function, the output lands between these parallel lines, somewhere between these parallel lines. So here, this satisfies it. Okay, so that's just really it, right? Someone gives me a challenge, and I need to respond. But I don't need to just respond once. I need to respond for any possible challenge. So if I get challenged with 1/10, then I have to get a certain amount close to A. But if I get re-challenged with like 1/1000, then intuitively speaking, I'm going to have to get closer to A in order to meet that challenge. And so the limit is L if you can respond despite whatever challenge you receive. Okay, and so finally, here we go. The answer to this, I'm going to now just state the definition. This is called the epsilon-delta definition of a limit. And it says that the limit as x approaches A of f of x is L, if and only if, and I'm going to do this in 3 different ways. Way number 1, casual. For all, this is true if for any epsilon greater than 0, no matter how small, I can respond with a delta, also greater than 0, such that, and now here's the claim about this delta. The claim about this delta is that if I stay on this interval, then my outputs land on this interval. So, so that for any x where x is between A minus delta and A plus delta, by the way, I don't want to talk about A, then the output of the function will be between L minus epsilon and L plus epsilon. Okay, I'll just say that one more time. This is just me giving you the definition, but this definition should flow from the conversation that we've been having. When we say that the limit as x approaches A is L, what we really mean is that for any possible challenge, for any tiny number epsilon, I can find a delta response. And what's true about this delta response is that for any x value in between A minus delta and A plus delta, but not A itself, then the output of the function for any of those x values lands between these 2 blue parallel lines. Okay, so that's basically good enough. But some of these English words, get kind of like annoying to write over and over again, and perhaps there's some ambiguity involved in using English words. And so what people do is not this. What people do is usually write this out, in more technical jargon. So let's do that now. And okay, we've seen this before, so this is not new. We use the upside down A for the quantifier. That means for all. And so so what we can say is that for all epsilon greater than 0, so this is just me saying the same thing over again, for any possible epsilon, there exists a delta greater than 0. In other words, there is a response, delta, such that, what is the claim I want to make about this delta? Well, once again, the claim is about all x values in between A minus delta and A plus delta. So for all x, and now we want to say if x is between a minus delta and a plus delta, then the function will be between L minus epsilon and L plus epsilon. Cha, cha, cha. Okay, and this is 95% good, but you need to sort of add in that, that x is not a, because I don't want to speak about what happens if x is a. So this is kind of maybe the best way of writing this. For any x in between a minus delta and a plus delta, if x is between a minus delta and a plus delta, then the output of the function is between L minus epsilon and L plus epsilon. Okay, there's even sort of just like one more level of rigor that you can descend into, and this is kind of preferable sometimes. And that is to say, okay, for any possible epsilon, there exists a delta such that for all x, so this is basically the same thing now, but instead of saying x needs to be between a minus delta and a plus delta, it's kind of convenient to speak about the difference between x and a. And so if you kind of bust out these absolute value symbols, then we can say the distance if the distance between x and a is less than delta. So now we're adding kind of like an extra level of sort of mathematical notation using absolute values. But don't be too scared of absolute values. The difference x minus a is just the difference between x and a. And the absolute values just ensure that it's positive, so we can interpret absolute value x minus a as the distance between x and a. So if the distance between a number and a is less than delta, then the distance between a number, between the output of the function and L is less than epsilon. So these are three different ways of saying the same thing. A lot of English words, fewer English words, and now sort of no English words, because even if then I've sort of expressed as like a kind of with a propositional logic connective. And okay, great. There's even one more tiny thing I can do, is that to account for the fact that I don't want to talk about x if it's equal to a, I can sort of change the antecedent of my conditional to apply only when the distance between x and a is positive. In other words, I don't want to talk about the case when the distance between x and a is 0, which is to say when x is a. Okay, so this is the definition that you will see in our textbook, this purple one right here. So maybe that's the one you should be more familiar with, but I think it's helpful to kind of linger somewhere around here. So this is maybe the definition that I'm gonna use most of the time. Okay, do you understand this? It's really hard to know until we really do one. So let's do one proof, and then we'll call it a day. Okay. Let's go. Yeah. So let me erase all this and. Okay. Let's go. Let's do the following proof. This is a simple limit. The limit as x approaches 4 of 2x minus 3. This is certainly 5. Okay, and in a certain context, it would be perfectly sufficient to just say, oh, it's 5, and just move on. But what we are going to do is we are going to prove that this is true. And we're going to prove it using the, I said it out loud, but this time I'll write it, epsilon-delta definition of a limit. And I might make like a little worksheet with 2 problems on it. So perhaps this will be the front. And then there'll be sort of 1 for homework on the back. Okay, let's go. Let's try to do this as casually as possible since it's our first time. So let's draw a picture. And okay, 1, 2, 3, 4. 2, 3, 4, 5. So boom, boom, sure. And yeah. What are we doing? Let's see, when x is 2, say, y is 1, and when x is 3, y is 3, and so we got something that looks like that. Okay, so it's a line. It's just a line, and the slope of this line is 2. And here is 4, and here is 5. And so the claim I'm making is so innocent. It's just that near 4, the outputs of this function are near 5. Okay, but based on this very low-level analysis that we've done, and you're entitled to be thinking, like, why are we even doing this? It's a really good question. But just trust me for a moment. So what are we really saying? Near for this function outputs numbers that are near 5. But the epsilon delta definition of the limit says, therefore, that what we really mean is that for any possible epsilon challenge, and so I'll now draw some horizontal red lines. What are the red lines? They're sort of how much you are allowing me to be off by. So this is 5 plus epsilon, 5 minus epsilon. Epsilon is the challenge. Epsilon is the dare from the sort of imaginary kind of person that I'm in a dialogue with. And the imaginary person is challenging me. My claim is that the outputs of this function are very, very near 5 when x is near 4. And the imaginary person says, how close to 5 are you? And I say, I can be as close to 5 as you want. And then this person challenges me with an epsilon. And I respond by getting as close to 4 as I need to get. So this is 4 plus delta, and this is 4 minus delta. And I do think it's important to do a little bit of kind of experimentation. So if you look at this line, so just imagine someone gives me an epsilon of, say, 1/2. What should my delta response be? Well, I think it's just kind of clear that if I'm only allowed wiggle room of 1/2 up and 1/2 down, then since this line has slope 2, any wiggling that happens on the x-axis is going to get amplified by a factor of 2. And thus, I am only allowed to wiggle by 1/4 in order that my output wiggle will be only 1/2. And so, okay, if you get that, good, and that means you just really get it. Okay, and similarly, if the epsilon challenge were 1/10, then my response is going to be, well, you tell me, right? If I'm allowed to be off by only 1/10 in the y direction, then since every error, so to speak, in the x direction gets amplified by 2 because the line has slope 2, then I'm allowed a wiggle of only 1/20. And this kind of common sense thinking suggests that there is a relationship between the challenge and the response. And it suggests that given a generic epsilon challenge, that my response should be half of that number. And yeah, that's just right. And actually the whole sort of difficulty in this proof is in determining what the challenge, what the response to the challenge should be. After all, you have completed this proof when you have shown that for any possible epsilon challenge, I have a delta response available. And so you have to have a response ready for any possible challenge. And so it's a game. Okay, we did this kind of thing last semester, right? Someone challenges me with 1/2, I respond with 1/4. They're satisfied. Someone challenges me with 1/10, I respond with 1/20. They're satisfied. But of course, they can kind of keep going forever, issuing me new challenges. And the only way we can ever complete this dialogue is by me considering every possible one of their challenges simultaneously via algebra. So I take a generic challenge, and I think I have just reasoned that that if whatever their tiny number is, if I just divide that tiny number in half,
then that describes how close to 4 I need to be to make this thing work. Alright, so we did that by just thinking it out and kind of being smart or something. But in general, the way you figure this out is via something called the discovery phase. And actually, before we do this, let's write out clearly what it even is that we're trying to prove. What are we actually trying to prove here? We're trying to prove that this limit is 5. Alright, but what does that really mean, to say that this limit is 5? Well, it means that for any possible epsilon challenge, so no matter how tiny of a number I'm given, that there exists some delta response such that for any possible x value, if it's between 4 minus delta and 4 plus delta, then the output will be between 5 minus epsilon and 5 plus epsilon. So if x is between 4 minus delta and 4 plus delta, but x is not actually 4, then the output of the function should be between 5 minus epsilon and 5 plus epsilon. This is what actually needs to be proved. I am here just kind of regurgitating the epsilon-delta definition of a limit that we developed, but as applied to this particular problem. So I need to show, for any possible epsilon, I need to provide the delta such that as long as I stay within delta of 4, the output of the function will be within epsilon of 5. Okay, and here in sort of parentheses, kind of just floating out here, is the fact that, let's just not talk about 4 itself. Okay, great. Well, so what's going to happen? I'm going to receive a challenge, and then I'm going to respond. Okay, and so then I'm going to prove that my challenge always works. This arrow means if then. Okay, so, the main thing then, the big sort of work that we have to do, just like last semester, is this discovery phase. What happens in the discovery phase? It's not really part of the proof itself. The actual proof is going to come next. But in the discovery phase, we need to discover what the appropriate delta response is. Okay, and sometimes it's obvious, like here it was kind of obvious, but it's not always obvious, and there is kind of an algebraic method to discover. And the answer is you work backwards, right? You say, okay, let's see. Someone's going to challenge me with an epsilon. I need to make sure my function is between these lines. So let's begin with the thing I'm trying to prove. So let's begin with my function between 5 minus epsilon and 5 plus epsilon. And then let's work backwards to discover how close to 4 I need to be in order for that to be true. Okay, well, what is the function? It's 2x minus 3. So this says 5 minus epsilon. So this says that the function 2x minus 3 is between 5 minus epsilon and 5 plus epsilon. Okay, so what I'm now doing is I'm playing around and I'm discovering for what x values do I land between the parallel lines. Okay, and now there's some sort of algebra 1 things that we can do here. We can add 3 to all 3 sides of this inequality. That gives me 8 minus epsilon is less than 2x, which is less than 8 plus epsilon. And now let's divide by 2. If we divide by 2, I get 4 minus epsilon over 2 is less than x, which is less than 4 plus epsilon over 2. And now, kind of just staring us in the face, is a statement that says, well, if x is between 4 minus epsilon over 2 and 4 plus epsilon over 2, then we're good. Okay, and the thing is that, right, the thing is that we're doing this with a function that's so simple, linear functions, and so kind of boring, almost, you could say, that it's just like too easy, or something like that. And so, because this function is so simple, that actually all the steps in this proof are reversible. And so since I started with the thing I was trying to prove and worked backwards, it only took me 2 lines. Now here I am, and it seems that this underlined green statement is telling me what I need to know. The answer is, hey, just stay within epsilon over 2 of 4 and all is good. In other words, this is telling me, the conclusion of this line right here is telling me that I should set my delta to be epsilon over 2. And of course, our conclusion here is the same conclusion we got over here by just kind of playing around and being smart and kind of thinking about it. But this is a kind of a more systematic approach to this. Okay, and so discovery phase concludes when you have algebraically determined by working backwards how you are going to respond. And the answer is, whenever I receive a tiny, tiny number, my response is going to be half of that number. Okay, now we finally get to the actual proof. What happens in the actual proof? Well, first someone challenges me with an epsilon. So take an epsilon greater than 0. This is how you do a proof in general. You want your proof to work for any possible epsilon. So take some epsilon challenge. How should we respond? Aha, well I have just learned in discovery phase that I should set my delta to be epsilon over 2. Okay, now all I have to do is show that it works. And so what I now need to show is, got to write kind of small here, I need to show that if x is between 4 minus delta and 4 plus delta, then the function will be between 5 minus epsilon and 5 plus epsilon. Okay, so I'll put a little red box around this because this is what I need to prove, right? Someone challenges me with an epsilon, I respond with a delta, and then the claim is that as long as I stay delta close to 4, my output will be epsilon close to 5. And okay, this is a conditional, an if-then statement that I need to prove. So the way to do this proof is to assume the antecedent and derive the consequent. So okay, so we should write something like assume that x is between 4 minus delta and 4 plus delta. And now I'm going to prove that everything works out. Well, I've chosen my delta so that it will work out. Okay, so delta is just epsilon over 2. So this is what I know. And now we just do it, right? Reverse all the steps. Multiply through by 2. So that gives me 8 minus epsilon and 8 plus epsilon. Sorry, I have to actually multiply by 2. And now, what's my function? My function is 2x minus 3. So I should subtract 3 from all 3 sides of this. And so that gives me 5 minus epsilon is less than 2x minus 3, which is less than 5 plus epsilon. And that's it, man. We're done. Because this function is in fact just 2x minus 3. And so I win. I've shown that, indeed, no matter what challenge you give me, as long as I pick my epsilon correctly, as long as I pick my delta correctly in response to your epsilon challenge, that specifically, whatever challenge you give me, I always I take half that number, and I get within that number epsilon over 2 of 4. Then, on the assumption that x is a number within epsilon over 2 of 4, then via like 3 lines of algebra 2 lines of algebra 1 really, I've just shown that my function is between 5 minus epsilon and 5 plus epsilon. So I met your challenge, and I did it for an arbitrary epsilon, and therefore for any epsilon, I've shown that I can meet the challenge, and therefore I've proven that this limit really is 5. Using this kind of fancy definition. Okay, whew. This was a little bit, some people like this, some people really kind of hate this. I will admit that it's like a little bit boring, so I thought maybe it would be better to just do it via video, and you can watch it kind of quickly, and we'll do one of these for homework, and that will be it. Goodbye.